Hi there, everyone. My name is Pranam Nalamar, and my research is on the Lanthanide database for abundances in neutron star mergers. Let's dig in. So, for the origin of the heavy elements, the heavy elements, so most notably the ones after iron, come from the R process, or the rapid neutron capture process, which is a process in which we have a bunch of atoms in a very neutron-dense region where they capture these neutrons, undergo beta decay, and that results in heavier elements formed. We see this in supernovae, but we also see this in neutron star mergers. The neutron star mergers are events that involve two dense balls of neutrons merging or combining together, and that is actually the densest region of neutrons in the entire universe. So it's perfect for the creation of extremely heavy elements, most notably the lanthanides and actinides. So this merger also results in an optical transient called a kilonova. And the kilonova light curve, it shows its brightness over time and is a direct result of all the R process elements that formed, but specifically the lanthanides. So how bright and what bands the kilonova peaks at is due to the composition and distribution of the lanthanides. So by studying its optical spectra, you can deduce exactly which elements were formed. So the motivation behind our research is that we not only want to understand the R process and how it results in all these different elemental abundances, but we also want to specifically focus on the different ionization state abundances as well as the isoelectronic state abundances in this merger material at late times. When I say late times, I mean from 1 hour to 2 weeks. And if you look over here, we can see in this plot that the distribution of the lanthanides, the lanthanide fraction, has a significant effect on the bolorimetric luminosity, the total brightness of the kilonova. So we would like to find out how the different ionization states abundances are distributed at late times so that we can then combine it all together and compare this data that we have to many of the neutron star merger and kilonova codes. So the reason we want to do that is because we want to measure this atomic spectra in a laboratory setting and then benchmark that with the stuff used in the neutron star merger and kilonova codes. So methodology and procedure. So we use Skynet, which is a nuclear reaction network code, which delivers all the elemental abundances that we care about from the beginning of the merger to a long time after. And this, combined with the Saha equation over here, details all the ionization state abundances across time and across temperatures that matter. So as you can see over here, we can see that the abundances of all the lanthanides don't really change too much in terms of order of magnitude. It's always around the same. Results and analysis. So based on our calculations that we've done for all the ionization state abundances between hydrogen and lawrencium, we chose specifically elements 1 to 103 because the NIST atomic potentials database that we used doesn't have anything beyond 103 in complete detail. That's why we focused on those elements only. And we saw that the ionization state abundances always had this kind of pattern where one ionization state dominates at a particular time or at a particular temperature. But specifically at early times, we saw that it's mainly fully ionized, and at late times, it's mainly fully neutral. So by combining all of these ionization state abundances together into one graph, we found out that there are 17 ionization state abundances or ionization states that matter at between 1 hour and 2 weeks. So in conclusion, we found out the distribution of the lanthanide abundances. We found out how the isoelectronic and ionization state abundances look, and we also found out the total dominant charge state abundances or charge states that matter at late times. We found out that the first 17 matter. More specifically, we found out from 1 day specifically to 2 weeks, we found that these three over here, the neutral, first, and second ionized states are the most dominant. Now, we also found out the calculations, we also did the calculations for the isoelectronic states, the number of them over temperature, and we found out that at late times, at low temperatures, that there were 14 unique isoelectronic states that contributed a significant amount of lines to the spectrum. And we determine whether or not it's significant based on a threshold value we set, which was 10 to the negative 6. So any abundance over 10 to the negative 6 was considered significant. And since there were 14 isoelectronic states, that pretty much confirms that there are 14 lanthanides of importance. And we would like to use this information that we gathered in order to make some sort of experiment where we can measure the opacity of a combination of all these different charge states of the lanthanides. Thank you for listening.